Tuesday, we talked about vectors in 3D, and we talked about electric forces. And I remembered one thing that I meant to say about vectors but forgot, which is that if in a previous course you've seen vectors written this way, then how does that relate to what we've been doing? Well, I, j, and k are special unit vectors. So I is the unit vector 1, 0, 0. It's the unit vector that points along the x-axis. And j is the unit vector that points along the plus y-axis. And k is unit vector along the plus z-axis. So what this comes down to is 3 times 0, 1, 0 plus 4 times, whoops, that's 1, 0, 0, 0, 1, 0 plus a minus 5 times 0, 0, 1. So we have 3, 0, 0 plus 0, 4, 0 plus 0, 0 minus 5. And that, of course, is just equal to 3, 4, negative 5 in our notation. So this is a cumbersome but equivalent way of doing it. Expressing it in terms of scalars times unit vectors and then adding them up. There's no particular advantage to this scheme, so we won't use it, but it's useful to know this just because you're going to run into it someday. See vectors written this way, and you need to know what they are. Okay. Any questions that you've thought of between Tuesday and now?
How was Norway?
Norway was awesome. Norway was so I was in Oslo, which is not as far north as you can get in Norway. There were like 6 hours of daylight, so the sun came up at night, it went down at 3. But it's a lovely city. It's a beautiful place, and the people at the University of Oslo are doing really exciting stuff. They've integrated computation not only throughout the entire physics curriculum, so all physics majors are doing serious computational projects, but they've actually Norway as a country has actually just mandated that computation will now be taught starting in grade 1 every year. So this is where we're all going. I mean, this is what needs to happen because computation is such a central tool of science and math. So there's actually a Center for Computing and Science Education at the University of Oslo, which is a collaboration between physics and math. And they're doing research and development. So it was great professionally, and it was really a lovely place. Norway is really advanced in terms of alternative energy too, so that just walking up the street to the university you'd find 5 Teslas parked in parking spaces because there's a big push to use electric cars. So it was very cool. Oh, and this reminds me to say I will actually not be here on Friday because I have to go to yet another conference, but this one's only in Florida, so it's so no office hours Friday. Okay. So let's just review slightly. Okay. So there's a sodium ion which exerts a force of 3 times 10 to the minus 8 newtons on a proton that's some distance d away. If we move the sodium ion so it was a distance 3d away instead, what would the force now on the sodium ion, on the proton be? So take a second and think about it, and then hold up the number of fingers corresponding to the appropriate answer. Talk to your neighbor. All right. Fingers, 5, 4, 3, 2, 1. Okay, mostly 4. 4 is correct because we saw that the electric force was proportional to 1 over the distance squared. And so if at a distance d the force was 3 times 10 to the minus 8 newtons, at a distance 3d this would be 1/9. So 1 over 3 squared times, so it would be 3 times 10 to the minus 8. Yes? What? The attendance sheet. Okay, that's not a question about the clicker question. All right. Okay, we have an alpha particle and a proton. Alpha particle has a charge twice that of the proton. They're 0.1 meter away from each other. Statement about the magnitudes of the forces the particles exert on each other is correct. Okay, what's the answer? 1, yes. They exert equal and opposite forces on each other. Reciprocity applies to electric forces. Okay, so today we're going to talk about the most important idea in the entire course. It's an idea that, a concept that we'll be talking about every day in some form or other. So this is probably the most important thing to pay attention to in the whole course. And it's the concept of fields. And here's the issue. We've seen that both gravitational forces and electric forces act at a distance. So objects, the very near the sun, and yet the sun is exerting a significant gravitational force on the Earth. A proton and electron can be fairly far away, and they still exert electric forces on each other. So these are two of the 4 fundamental interactions that occur at a distance. How does that work? I mean, how does the Earth know that there's going to be a spacecraft here 1 millisecond from now, so it knows how to exert a force on that spacecraft? How do things manage to exert forces at a distance? And is it instantaneous? I mean, if the spacecraft moves to here, does it instantly? So how does this work? How do a proton and electron manage to influence each other at a distance? And it doesn't really matter where they are, they're still going to affect each other. So the question is, what's going on? And furthermore, this instantaneous thing bothers people a lot, and it should, because we know from what Einstein hypothesized in all of our experiments that information can't travel faster than the speed of light. So communication isn't instantaneous. So if the spacecraft moves to here, how can there still be a force on it? Okay. So the basic idea that was evolved to explain this, and it's a little abstract, but it turns out to be an extremely powerful idea, which is why we're going to spend the semester exploring it, is that a massive object like the Earth fills all of space out infinitely far with what we call a gravitational field. And it's sort of, you can think of it as, it's almost like this giant spider web of invisible field waiting for something to come along and be affected by it. So at all times, surrounding any massive object, the Earth, the Sun, the Moon, a galaxy, there's a gravitational field throughout all of space associated with this massive object that lies in wait for another massive object to come along and be affected by it. Now here, notice that we are implicitly doing what we did last semester and dividing the universe into two pieces. There's the system and the surroundings. So the thing that's being affected by the field and experiencing a force, that's our system. And the surroundings would be all of the massive objects that are making fields that affect it. Okay, so we're back in the system and surroundings situation. Okay, so what do we know? What can we just sort of, and you've heard the term gravitational field before, right? Yeah. Do we know about what has to be true about that field? Well, since massive objects are always attracted to each other, field must have some kind of a direction. Because if we put a spacecraft here, it's going to feel a force that way. But if it was over here, it would feel a force that way. So there must be it must be a vector quantity. It must have a direction. And it can be stronger or weaker. It's probably stronger near the Earth and weaker farther away. The gravitational force you saw depends on 1 over distance squared, just like the electric force does. So probably it must look like the Earth or any massive object is filling all of space with a field that has a direction, so it must be pointing toward the Earth, since that's going to be the direction of the force on a massive object. So we could draw a picture that said, at this location there's a gravitational field pointing that way, and at this location there's a gravitational field pointing that way. And if we wanted a symbol for a gravitational field, we could actually use little g, but as a vector. So it could get, now, and it probably is smaller when we're farther away, right? Because the forces are going to be smaller. So we define the direction of the field as the direction that another massive object would feel a force. Okay? So you can think of this space around the Earth or around the Sun as filled with this gravitational field that's going to pull things, or a black hole, very strong gravitational field near a black hole, and to pull things toward it. And it gets weaker as it gets farther away, but it never really quite goes to zero. although at some point we may be able to neglect it if we get far enough away. Now, charged objects kind of interact at a distance too. So no matter what the distance is, we can calculate a force between two charged objects. Charged objects have a behavior that's a little bit more complicated, though, because they can attract each other or repel each other. So the field around a charged object must actually depend on the sign of the charged object. So let's see if we can sort of figure out what it would look like. So suppose we have a positively charged object here, a proton. If we place, now we had to pick something about a convention for directions of fields. So the convention is that the field around an electric field points in the direction that a positively charged object would feel a force. Which would mean that if we put another proton here, it would be repelled by this proton, right? So it must be that the electric field, which the symbol is capital E, and it is a vector, due to proton 1 must point away from it. And if we put a proton over here, it would be repelled. So we'd say that we know that the electric field over here must point that way. And up here, it surely must point up. And down here, it points down. And if we're farther away, it's going to be smaller. So let's go twice as far away. So it should be a quarter as large, presumably. So okay, so that's a field around a positive charge. What about the field around a negative charge? So here's an electron. Now we're defining the direction of field as the direction a positive. So it's this location. What do we deduce about the direction of the electric field surrounding this negative charge? What's the direction a positive charge here would feel a force? It's going to be toward the negative charge, isn't it? So in this case, so this is object 2. And likewise over here at this location. And you can see that we need to be very careful about talking about the electric field at what location. Because since it changes in direction and magnitude with position, when we talk about electric field, we have to be very careful to specify what location in space we're talking about. And if we were able to measure the electric field up here, it would be like that. And I'm trying to make all these locations the same distance from our electron. And the location, and so we get a different pattern of electric field around a negative charge than we get around a positive charge. It would have some similarities. It'd be spherically symmetrical. Magnitude decreases with distance, but the direction. Now, when we measure the electric field, and we'll talk about how we do that in just a second, we measure it at some particular location in space because it's different everywhere. And so the location at which we measure it is called the observation location. That's where we're measuring the field, where we're interested in the field. And so at this observation location, we'd get an electric field of this magnitude. If we go twice as far away, we get an electric field that's a quarter as large. Okay, so it's a different observation location. And since we're saying that the force on a charged object that happens to be at this location is going to depend on the electric field, and surely it's going to depend on the charge of the object we put there also. The force between two massive objects depends on the mass of the objects. Okay, so the force on the object that's our system, the thing that's being affected, depends on two things. It depends on the charge of the system, the proton or whatever it is we're putting there, times the electric field made by the surroundings. And this is basically our definition of electric field. Now, how would we measure field? Well, we'd put a charge somewhere and measure the force on it. So we will often, in a thought experiment, consider, and we put the charge, you want to put a really small charge there so it doesn't make the surroundings rearrange very much. And so our thought experiments will involve a proton attached to a spring, and that'll be our little test charge, and we'll put it somewhere, and we'll see that our spring stretches this way. So basically we could measure an electric field by just measuring the force on the system and dividing by the charge of the system we put there, and that would give us a way to determine an electric field at a location. So let's think about this, because one interesting thing about this is that if we're able to measure an electric field, if we somehow know we can calculate or measure an electric field at some location in space, we can predict the force that any charged object will experience there. If we know the electric field, then we could tell what the force on a proton would be, or an electron, or an alpha particle, or a ping pong ball with a charge of -3 microcoulombs. Okay, so it doesn't matter. If we know the electric field, then we can predict the force on anything. So it's convenient too, in terms of calculations. Once we know the field, we know the force on any object. So for example, suppose at some location here, we've measured the electric field with our little proton on a spring, and we know that at this observation, the electric field is let's say it's 6,000, 4,000, 0, and what are units of field here? What do they have to be from this equation? Newtons over coulombs, that's right, because this is newtons. So this is newtons per coulomb, because that's newtons and that's coulomb. So what would happen if we put a proton here? at this observation. We don't, now notice that if we know the electric field here, we don't have to know where the charges making that field are. So there are a whole bunch of possibilities. We could certainly have a positive charge here making that field. What's another possibility? Could there be a charge here making the field? What would its sign have to be? It'd be a negative charge, wouldn't it? We could have a positive charge and a negative charge. We could have, okay, so there are a lot of possibilities, but we don't have to know where all those charges are if we know what the field is at some location. So the force on the proton is just going to be the charge of the proton times the electric field, so that's 1.6 times 10 to the minus 19 coulombs times 6,000, 4,000 newtons per coulomb, which gives us a 9.6 times 10 to the minus 16. And what is it, 6.4 newtons. So if we put, this is the electric field, if we put a proton here, force on a proton. Now notice that although I can draw both electric field and electric force on the same diagram, they have totally different units. So therefore the scales are some arbitrary scale factor in drawing them both on the diagram. What if I put, instead of putting a proton there, what if I put a charge that had a negative 6 microcoulomb charge? So we took a ping pong ball that we'd rubbed with wool that had a charge of spread out all over its surface, negative 6 microcoulombs. Well, that force would be negative 6 times 10 to the minus 6 coulombs times 6,000, 4,000 newtons per coulomb, and that's going to give us what, 36 times 10 to the minus 3.6 times 10 to the minus 2. So we get a minus 3.6 times 10 to the minus 2, a minus 2.4 times 10 to the minus 2, 0 newtons. And of course these aren't drawn to the same scale because this force is so much bigger than that. So to draw that to the same scale, whatever. But you get the idea, right? Yes? That's the charge on our ping pong ball that we're putting here. Which negative 6? That's micro. That's a mu for micro. So micro is 10 to the minus 6, right? Yeah. So I mean that would be if instead of putting a proton here, we put a ping pong ball that had a charge of negative 6 microcoulombs here. Okay. So we could just keep putting things here and taking them away, and every time we did that, we would be able to calculate the force we expected on the object. All right. So 13.3. Okay, so at some location, A, which is our observation location, we place a proton. And we note that the proton starts moving in the direction shown. What can we conclude about the electric field due to the surroundings at location A? Remember that you're allowed to talk to each other.
So what I think.
Exactly. Thank you.
Because there's only two possibilities.
How something's positively charged is going to go.
Yeah. Yeah, the electron will go there. Alright, cool. Good talk.
Okay, what's the answer? You need two hands, maybe. Might need. 8 is correct. So because this is a vector equation, it says this vector, the force vector, is in the same direction as this product, which could be the direction of the electric field, but we need to check and see if this is positive or negative to see if it flips a direction. Okay, so indeed, if we know the force on a positive charge is in that direction, then the electric field must be in that direction. So that's correct. At location C, this is a different location, we've made a measurement and we know that there's an electric field at that location in space, and there's an electric field everywhere else to that location. So the electric field is in the direction shown. We put a chloride ion at that observation location. What do we predict the direction of the force on the chloride ion by that electric field is going to be? Think for a minute. Talk to your neighbor. Okay, so what do you think? 2, I agree. Yes. So in this case, the force is going to be opposite to the direction of the field because the charge that's being affected by the field is a negative charge. Okay. So charged objects make fields, and we know that charge is quantized. So something that's got more than, it's negative, but it's got more than the charge of a single electron must just have more electrons. So if we could figure out the electric field, a mathematical expression for the electric field made by one single point charge, then we could just use superposition to add up the contributions of all the point charges around and get the field due to any arbitrary collection of point charges. So we know that that two charges, and let's not even specify their charge, they're just Q1 and Q2, they could be positive, they could be negative, but we'll say this is the system and this is the object in the surroundings. that's responsible for making an electric field that affects the system. And if we were gonna calculate that force, we'd draw the vector r from the source of the field, we're gonna say, to the system that's being affected by the field. And then we could calculate the force on 2 is going to be 1 over 4 pi epsilon 0 q1 q2 over the distance, which is the magnitude of r squared, times the unit vector r hat, which points in the direction of r. But we also know that the force on the system is equal to the charge of the system times the E of the surroundings. Just rewrite this a little bit. We could write this as Q2 times 1 over 4 pi epsilon 0 Q1 over the magnitude of r squared r hat. So this is the charge of the system. So this must be the electric field made by the surroundings. In this case, the surroundings are very simple. It's one other charged particle. So it looks like the electric field made by a point charge is going to be 1 over 4 pi epsilon 0 q over the magnitude of r squared r hat, where the vector r now goes from this thing that's the source of the field to the observation location, to the location where we want to know the field because we think a charge might come along and be affected by the field there. So this is really the same calculation we've been doing. We're just not including the thing that's being affected. So this is the charge of the electric field of the source, the charge of the point charge that's making the field. So what does this look like? Okay, so if we just calculate the electric field due to a point charge, this is one of the demo programs. We see here, let me make it just a little bit smaller, okay, that if this is a positive charge, then we calculate the electric field at a bunch of locations on a circle surrounding that, and we get an electric field pointing away, which is what we knew, and we're just using that equation to calculate it, where r is the vector. In each case, for each observation location, we need a new r. So for this observation location, we draw r that way, and then we get r hat, and then we calculate it. And then for this observation location, we draw r that way, and we get a new r hat and calculate that. And then if we double the distance and do that whole thing again, we see that it... Now this is obviously a 2D slice through what's a very 3D thing, though. So it would get visually complicated if we did it at a lot of locations, but we can at least do it on 2 perpendicular planes, and we see that as we rotate, there's an electric field that's spherically symmetric around this point charge pointing away from it. So what would happen if, what would it look like if it were a negative charge instead of a positive charge? Should point the other way, shouldn't it? So if we make it negative charge instead of a positive charge, we still see the same distance dependence, but now the field made by this charge is pointing toward the charge. And if we look at it in 3D, we see that now sometimes people ask, is the electric field that's made by a positive charge somehow different from the electric field that's made by a negative charge? The answer is no. An electric field is an electric field. It does exactly the same thing. It exerts, once you know the electric field, it doesn't matter what the source was. Everything reacts the same way when it gets put in. But that's what we've got. And this electric field is, let's see here, wait, I know where this is. There. Okay. So the electric field is everywhere in space, so that if I have a point charge making electric field, if I move it around, we see that the electric field everywhere in space around this charge changes. And it's really big close to the charge, and it's really small far away. So even though in our representations we're drawing we're only a few arrows, we still have to think of this field really filling the entire volume of space around a charged object. Okay, so here's our source. This Q1 is a source of the electric. And at any observation location, we can use this equation, if it's our source is a point charge, to calculate the electric field due to that point charge. What's the electric field made by that point charge at its own location? So here's a source, here's a point charge. It's the only thing around. What's the electric field right here? So is it 0? So what happens if magnitude of R goes to 0? It would be infinite, wouldn't it? So basically we say that there's a singularity because we can never quite get there, right? So we say that the electric field is undefined due to a charge is undefined at its own location. And that makes sense because it can't affect itself, right? I mean, it couldn't exert a force on itself. So it gets very, very big as we get closer and closer to the charge. But we don't define an electric field, a value for the field at the location of the charge. Okay. So, so just for the heck of it, let's calculate the electric field due to a charge at some location. This should be getting to be an incredibly familiar calculation. So let's see, what do we have? We have an electron and and we want to calculate the electric field due to this electron a distance of 1 times 10 to the negative 6 meters, so a micrometer away from the electron. And we'll make it on the x-axis just to make our life simple, okay? So what's the first thing we need to do? We need what? We need the charge. The charge of an electron is negative 1.6 times 10 to the minus 19 coulombs. So we know that. What else do we need? What? What did he do?
Define the system and surroundings.
Define the system and surroundings. Perfect. Okay, so there kind of isn't a system here, is there? Because we haven't put anything there to be affected by the field. So system and surroundings, right now what we're doing is calculating the effect of the surroundings so that when we do decide on a system to be here, we can calculate the force on it. But right now, so that's an interesting point. Well, we're going to use this equation. So Tristan's right, we need the charge, we know that. We need the value of 1/4 pi epsilon 0, we know that. What else do we need? We need r hat, well, and we're going to need magnitude of r, so we better find r. Now the definition of r in this case is that it goes from the source of the field to the observation location. So how do we draw r? Yeah, it starts at the source and it goes to the observation location. This is r, and what is this vector? Yeah, it's negative 1 times 10 to the minus 6, 0, 0. And so we know Q is 1.6 times 10 to the minus 19 coulombs. We know 1/4 pi epsilon 0 is 9 times 10 to the 9th Newton meters squared per coulomb squared. So now we need r hat and r mag. So what's the magnitude? What? Thank you. You guys should catch that. So what's by inspection? What's the magnitude of r? Yep. So we're going to square all of these things and add them up, and and then take the square root. So this squared square root is just going to be 1 times 10 to the negative. By inspection, what's r hat? R hat is negative 1, 0, 0. And so the electric field is 9 times 10 to the 9 Newton meters squared per coulomb squared times a negative 1.6 times 10 to the minus 19 coulombs divided by 1 times 10 to the negative 6 meters squared in the minus 1, 0, 0 direction. And we do some arithmetic and we get a plus 1440, 0, 0 newtons per coulomb. And so that looks like the electric field at this location is in the plus x direction. Is that right? Is that what it should be? So notice that the direction of the electric field depends on two things here. It depends on, and r hat actually was pointing that way, but it also depends on the sign of the source charge, which was negative, and so two negatives multiplied together, we got a positive in the electric field. So how would we calculate the force on an alpha particle? That would be our system. Suppose we now have a system to be affected. We just multiply by the charge of the alpha particle, right? And we're good. Questions about this? So it's simple, but it's fairly deep, and we're gonna yes.
Is this where like the pi and 1/4 pi epsilon comes from?
So the 4 pi comes from the spherical geometry, the whole 4 pi steradians thing. That's why that's in that constant. Okay, let's see if we can answer a few questions. What do I want? E. Okay, so what's the answer here? So I'm saying 8. And that's correct. So if we had an electron here, it's a negative charge. It would make an electric field everywhere in space that pointed toward itself. And so in fact, at that location, the electric field. So if we actually now put an electron at this location, what would be the direction of the force on the electron due to that electric field? Yeah, 4, it would. Okay. Okay, you put an electron somewhere in space, and you observe that there's a force on it, electric force on it in the direction shown. What can you conclude about the direction of the electric field due to the surroundings at location A? Yeah, all right, 4, that's correct. Yep. Let's see. Here's the thing about conventions and drawing arrows representing vector quantities that's actually important. This is a convention we agree on. It's a communication thing. So there's an electron at location B. We've calculated the electric field at A. Oh, sorry, it's a proton. Proton at location B. We've calculated the electric field at A, location A, due to the proton. And now someone asks you to draw the electric field at A due to the proton. How do you draw that arrow? Where do you put the tail of the arrow? Okay. Yes. Yeah, you're going to put the tail of the arrow at the observation location, at the location where you calculated the field, because that's where we know the value. The value of the electric field at location B is either infinite or undefined. So what we're going to do here is to communicate what we've that's the location where we know the field. So here's our source. We've calculated the field here. To draw the field we've calculated, we need to put the tail at the observation location. To show that that's the location in space where we know the field.